All right, good morning. Good morning. It's still morning, right? Yes, it's morning still. That is great. How has everyone doing today? Has anyone been outside? It's crazy outside. What is going on out there? Yeah, I know. What the heck? It was so nice like yesterday. Well, 2 days ago. It wasn't really that nice yesterday. It was kind of cold yesterday too, but I'm like, my office has like, I'm right beside the window and all I can hear is like the wind going crazy. Okay, let me get hydrated up and we will get this party started. Okay. Some of my past students were like, they know that I have invested in Bitcoin. So they've been emailing me all excited this morning because apparently Bitcoin has reached an all-time high, which is kind of fun. That's a fun way to start a Monday morning. I can't retire. I've only made like $400. I didn't uh, I didn't invest that much. I mean, I've invested about $1,000, and yeah, it kind of grew up to, well, I don't know where like, has anyone checked? Has it passed 40,000? I only have like 0.02 Bitcoin. Like I have very little Bitcoin, but I have enough that like I've made a sizable return on my investment, which is kind of fun. 55? Holy crap. That's insane. I remember like, I'm pretty sure the last time, yeah, no, Ethereum, yeah, Ethereum has reached some pretty good highs, I think, as well. I have a little bit of money in Ethereum as well, which is kind of fun. So yeah, it's been nice to check in on the portfolio several years later. I don't know if you guys remember, was it in 17 or 18 where went kind of crazy as well? And I like had bought a whole bunch back when Bitcoin was like 22, 23,000. So it's been fun to kind of watch it grow over the last. Don't invest in that coin, please. Don't invest in that, Nathan. There are better coins to invest in than Dogecoin. All right. How were your weekends? Was the weekend good? Did you get a chance to like enjoy that awesome weather we had? Yeah. That that coin though, like it's nothing. Like if you invest into that, you don't really, I mean, unless you're going to day trade, you don't really get anything in return, which I think is hilarious. Yeah, that's awesome. So the slopes are still doing really well. We had some really nice like sun over the weekend too, which was sweet. How was integration by parts? How did IBP treat you guys? Did you get a chance to check out that little recording? A couple thumbs up. That's good. That's good. Let's just do a quick little recap. So we've looked at the substitution rule. Substitution rule is the reverse of the chain rule, which is ironic that that one comes first because chain rule is the hardest differentiation rule, in my opinion. And the integration by parts rule undoes the product rule. Now, to be completely frank, you don't really need the quotient rule because you can always move the denominator up into the numerator and think about it as a product. So we don't have a technique to undo the quotient rule because all quotient rules are just fancy product rules. So we took a look at the product rule, set up some integrals using fundamental theorem of calculus, and we popped out the following formula. So this is our shorthand formula for integration by parts. And the idea is it essentially allows you to take a product of things and kind of degrade away or kind of erode away one of those terms in hopes that you're going to get a simpler integral to work with. So we looked at a couple examples here, like x sine x. We picked x as the thing to try to erode away by taking its derivative, and we're left over with integral of cosine x, which is a lot easier to think about and solve. So that's the power of integration by parts. It essentially allows you to do a swap out of some stuff in hopes that you're going to get a simpler integral in return. So I promised you a few more examples. Oh yeah, we did the integral of the logarithm in arctan. How fun is that? So now you guys have like lots of firepower, right? Like if you ever need to integrate these things for some reason, you got formulas for these. Bada boom. Let's continue on the formula train. I'm sure you're probably curious about how to integrate something like secant. I mean, I'm curious. Sometimes I like look online and I'm like, how in the hell is that the antiderivative of this function? This one's weird. This one's not integration by parts, by the way. It's more of like a weird, clever substitution. So, but I want to essentially look at a really cool integration by parts formula next. So this is, I guess, maybe like a little aside to get us to where we need to go, because we eventually want to be able to look at these kinds of integrals, you know, any power of secant or any power of sine, and be able to develop a formula to integrate those kind of tricky things. So this one starts in the following way. It says, consider the leap of faith by multiplying secant by the following expression. Now, this is not something that I would expect you to know how to do without looking it up or me showing you. So please don't be worried that you're going to have to be like this clever with integrals. We don't usually have to be this clever in calculus, second part of calculus, but this is what we do with secant. We essentially multiply by 1. So we're multiplying by secant x plus tan x over itself. So we're multiplying by the number 1. And we're going to make this integral a little bit more complicated, but also a little bit easier to deal with. I feel like that pirate meme, like, yes, but actually no. Okay, so in the numerator, if we distribute secant through the numerator, we get secant squared plus secant x tan x. And we're going to leave that denominator as is, as secant. And you know what I'm going to do? I'm just going to rearrange the order, so maybe some of you will be able to see why we did this. Okay, so I've arranged the denominator in a very seductive way in hopes that you guys will be able to see why this multiplication in green is interesting. And it goes, whoops, it goes like this. What's the derivative of tan x? You know the derivative of tangent, right? That's interesting. What's the derivative of secant? You guys know that derivative, right? That's interesting. So it turns out by multiplying by this weird green fraction, you get the derivative of tan plus the derivative of secant. So we basically set ourselves up for a substitution. Okay, we're going to take u is equal to the denominator. And we do that because we notice that the derivative of the denominator is actually inside the numerator. Okay. So in other words, I can take this secant squared x plus secant x tan x, multiply that by dx, and all of that becomes du. So this whole integral turns into a super nice one that looks like this. Okay, our denominator becomes u, and our numerator becomes du. Goodness gracious. Who would have thought? Okay, we have definitely converted this into something that you should know by now, the integral of 1 over u. Don't forget your absolute values. It is important here. Okay, we're going to take the antiderivative of 1 over u. That's the absolute value around the u inside of our natural logarithm. And then we'll do a backwards substitution to get x back in. So we have the natural logarithm of tan x plus secant x. And there you go. There is the antiderivative of the secant function. And like I said, the absolute value bars will be important here because tan and secant could, this sum could be negative. So yeah, we just have to be careful about that. So absolute value bars, definitely yes. And there you go. Now you have a formula in case you encounter secant anywhere. You know that this should be the natural logarithm of some gross stuff plus c. There you go. You can add that to your, hopefully you have like a little sheet of common integrals. That would be helpful. Add that to the sheet. Add that to the pile. Okay, what do I want to do? What's secant and cosecant? Okay, let's write out the integral for cosecant as well. Okay, this one's going to come out to be -1, I think. Yes, so this one will come out to be negative ln cotan plus cosecant. Now, I'm going to put a little star here. If you would like, maybe you would like to prove to yourself that this is true. So use this example that we just did. See if you can figure out what to multiply by to get the substitution to work. So I'll leave that one in your ballpark. You can take this, it's part of our notes. You can take this as fact now. But if you want to try on your own, then go for it. Just not now. Okay, so that's going to end our little aside. And now we're going to get into kind of the big chunker today, and this is what we call the reduction formulas. And my focus today is going to be working on some of the trig functions. So I'm going to maybe prove a couple of these and show you how to execute them in practice by hand. But there are other forms as well. So, I mean, I'm going to work mostly with the trig functions, but there's lots of other kinds of forms, lots of other kinds of reduction formulas as well. So Like I said, my focus will be trig functions, but there are other functions that have reduction formulas too. So they help us take powers of trig functions and reduce the powers. Okay, so we're going to prove a reduction formula for secant. And I think I'm going to kind of run out of room here. So let me move this down here. And we're going to add to that. Okay, so the formula is, if I want to find the integral of secant, okay, so if I want to find the integral of secant to some power, we can use integration by parts to get kind of this piece here, which is 1 over n minus 1. So this is a constant number, 1 over n minus 1, times secant to the n minus 2 times tan. So this is that uv part, essentially, in the integration by parts formula. And then I'm going to get a brand new integral. There's going to be a constant in front of this integral. The constant is n minus 2 over n minus 1. And the new integrand we get is secant to the n minus 2. So the idea here is if I have a large power of secant, I can use this formula to reduce that power until I get to like secant squared or just secant by itself. And then I have the capacity to be able to integrate that resulting integral. So let's try to prove this using integration by parts. And then we will see how to apply this to maybe secant cubed and secant to the power of 4. Okay, so let's try to set up an integration by parts and see how this is going to work. Should I take a single secant or should I take 2? I could probably take 2 secants. I could probably take a secant squared and integrate that. That's probably the easiest. Yes, okay. I have a game plan. The game plan looks like this. I'm going to think about our starting integral in the following. I'm going to think about it as secant to the n minus 2 times secant squared. And the reason I want to do this is I'm trying to look into the integrand here and see what's easy to integrate. A single copy of secant won't be helpful for us to put as dv. So essentially, I'm trying to kind of think about what are the 2 pieces I need for my integration by parts. If I have a single secant, that's gross because a single secant is going to give us the natural logarithm function. We don't want that. So what we're going to do is we're going to take secant squared instead. I know how to integrate that. The antiderivative of secant squared is the tan function. Okay, so here, this is what we're going to take as our dv. We're going to take the secant squared dx as our differential dv. And that means the leftover stuff is going to be u. Okay, so we're going to think about u as secant to the n minus 2. And now we have a potential way to set up this integral. So let's go through the process of integration by parts and see if this is helpful. Okay, let's begin with secant x because that's the easy side. or secant squared, I guess. So taking the antiderivative of secant squared, we get tan. And this is essentially where this tan comes from up here, okay? So that's why that tan is kind of popping out in the middle of nowhere here. Okay, next, let's take the derivative of our u bit and see what we get. So du by dx is, okay, we are going to have to apply the chain rule here. So just be careful. This is going to be n minus 2 secant to the n minus 3 times the derivative of secant. So I'm going to move some stuff over so I can write it all out on the same line for you guys. It looks a little messy right now. Okay, so bring my power down, n minus 2, secant n minus 3 times secant tan. I still don't have enough room. Goodness. Okay, you go over here. Now we can combine the secants that we get from taking the derivative. Okay, so we get n minus 2. Adding that secant back in, we'll get secant n minus 2. Okay, and then we need to solve for du. So du is going to be this awful expression here. Okay, so the four pieces we need, u, v, and du and dv. So those are the four bits that we need here in order to make integration by parts magically happen. And here it comes. Okay, so our resulting integral should, or sorry, our resulting expression should be uv minus integral of v du. Okay, so let's give it a shot and see what happens. So uv minus integral of v du. That looks nasty. But it definitely looks like some stuff that we need is popping out, so that's nice. Let's see, did I make a mistake somewhere? I don't think so. Still, I'm curious about where this n minus 1 comes from. So let me clean this up and see if I can kind of get a path forward for us without having to look at the integral calculator. Okay, let's pull that constant out front. And inside here, we're going to have secant n minus 2 tan squared. Oh, okay, I think I see. Maybe, let's see. Tan squared. Tan squared. That feels like a Pythagorean identity to me. Yeah, that feels like a Pythagorean, and we can change that into something, can't we? So what is that? I'm going to look up that Pythagorean identity. I always forget the tan one. So tan squared plus 1 is equal to secant squared. So that's what I think might be helpful here. So tan squared plus 1 is equal to secant squared. So in other words, tan squared is secant squared minus 1. Okay, that should be helpful. Let's give that a go and see what happens. And then let's vow never to prove another one of these formulas again. Okay, so changing tan squared into secant squared x minus 1. And then we're going to essentially expand through the brackets here, okay? Okay, so I should get integral secant to the n minus secant n minus 2. That's nice. Hey. Good. That's what I want. Okay. Problem solved. Okay, I'll let you guys kind of get caught up and make sure that working with the powers here makes sense for you. The next step, if you want to kind of truck on ahead, is to break apart the integrand into two integrals. And we're going to be adding the secant n's together. And that's where we're going to get this missing n minus 1 factor, I think. Again, please don't be like super intimidated about this. This is not something that I would ever ask you to recreate on an assessment. I do expect you to know, I'm doing this for interest, right? So some of you might be curious as to how we can use integration by parts to do something that's beneficial. And I think these reduction formulas are beneficial. What I really want you to understand is how to utilize these reduction formulas in practice, because they will come up a fair amount in our course, I think. Or at least it's nice to have these as tools. Okay, here's how we tackle the rest of the question. So we started with secant n. We showed that that should be equivalent to secant n minus 2 tan minus n minus 2 integral secant n plus n minus 2 integral secant n minus 2. So this is that breaking apart of this singular integral into 2. And I'm going to highlight the things that we need to add together. So I need to add these two things together. Okay, so let's combine them over on the left-hand side. Just about there. Okay, so I have one copy of integral secant n plus n minus 2 copies of integral secant n. Adding that together, we have 1 plus n minus 2 copies, or we have n minus 1 copies of integral secant n. Okay, so 1 copy plus n minus 2 copies should give us n minus 1 copies all together. Okay, so over on the left-hand side, we have n minus 1 copies of the original integral that we wanted. Over on the right-hand side, we have this really awful expression. And the last step is to divide both sides by n minus 1. Holy crap. There you go. That is how you use integration by parts and a little bit of algebra to prove the following formula. I will never ask you to prove this formula. That's not going to happen. But what I might do is I might ask you to use the formula to evaluate or find an antiderivative of something. So let's look at how to apply a reduction formula. And I'm not going to go too crazy on the powers here because I don't want to have to use the reduction formula several times. But this will give you an idea of eventually, because of the cascading powers, we will start at n, whatever that number might be, and we're always subtracting 2. So eventually we're going to land on either secant squared, if the original n was a positive number, or we're going to land on secant by itself, a singular secant, if n was an odd number. You know the integral of secant squared, its antiderivative is tan. And at the start of class today, we looked at the integral of secant, which is that weird logarithm function. So now you can integrate essentially any power of secant. So let's start with secant cubed. The first thing you want to do is identify the power. You want to figure out what is n, and then we're just going to use the formula. We're going to like move over to the right-hand side and just fill it in, whatever that number might be. So we're going to use the formula with n is equal to 3. Okay, applying the reduction formula, we get 1 over 3 minus 1, secant 3 minus 2. 3 minus 2 over 3 minus 1, and secant 3 minus 1. Okay, so just fill in, essentially we're just filling in 3 everywhere we see n in the formula, that's all. Okay, so all of those numbers that I've highlighted need to line up. And then we just start working away at simplifying some stuff. So 1/2 secant x tan x plus 1/2 integral secant squared. Okay, so notice that we've started with a power of 3. We've applied the reduction formula once. Oops, I think I did something wrong here. This should be 3 minus 2. This should be a singular secant. I've applied the reduction formula once, and now I get integral of secant. This is something we know how to solve from the start of class today, so we can finish up this particular problem using the antiderivative found earlier. Okay, so that's going to finish off the first part. Okay, I'm just going to zoom out a little bit so you can actually see the reduction formula. And like I said, this last little bit moving from here to here. This was done at the start of class. Okay, how are you guys feeling so far? I know that the reduction formulas tend to be kind of big and a little overwhelming. Does the example help? Is that a helpful thing? Oh, Colin, what a good question. What a great question. The answer is, I mean, the formula I gave you only works for secant, but I will give you lots of other formulas today, so don't you worry. We got lots of reduction formulas. Especially, I want to give you the trig reduction formulas today. So yes, you're going to have a slew of formulas, probably 4 or 5 formulas just for, I want to give you sine, cosine, tan, and secant. Those should be the 4 that we need. And then we should be able to pretty much do anything we need. By the way, you can find a lot of reduction formulas just by typing in reduction formula into Google. So I just did this, and I found a really cool page that has 34 different reduction formulas, which is kind of cool. Another thing that I know Stuart, the textbook, usually does is at the back, there's usually like a little tear out page at the back that has a whole bunch of the formulas for integral calculus. So if you do have a hard copy, that's your cheat sheet back here. You can always use those integral tables is what we call them to get your reduction formulas. They should be in the textbook. Okay, second one. Let's see how this works with a, let's say, a secant to the power of 4. So it's same kind of story. I'm just going to identify n. So in this case, n is equal to 4. And I'm going to utilize that reduction formula. Let's see if I can do this. Just being mindful that everywhere I see n, I need to put in the number 4. Okay, once you've done that, just start working away at simplifying this expression. We're going to get 1/3. And then we should get a 2/3 here. Okay, and we're left on the right-hand side with a secant squared. And we know how to find the antiderivative of that. That's just tan. So there's number 2 all sorted out. So that's how we apply the reduction formulas. If you see something that looks kind of nasty, it has a power, there's probably a reduction formula to start decreasing that power a little bit and getting it into a form. Essentially, we're trying to get it into something that you have inside your list of common integrals, essentially, right? So in this case, trying to reduce the power till we get to secant or reduce the power till we get to secant squared. Now, Colin has asked for other reduction formulas. So yes, I would like to give those other reduction formulas to you. Okay, let's start with the sine reduction formula. So if you are met with a really nasty integral that is a power of the sine function, you can reduce the power in the following way. Okay, -1/n. This is sine to the n minus 1 times cosine. Plus n minus 1/n, and we get a decrease in that power by 2. Okay, so sine to the n minus 2. So there is your reduction formula for the sine function. Okay, powers of cosine tend to come up quite a bit as well. So let's do a cosine reduction formula. Okay, so it looks very similar to your sine reduction, just with a change in power and a change in sign, right? So 1 over n instead of negative 1 over n. 1 copy of sine, n minus 1 copies of cosine, and the same fraction over here, so n minus 1 over n. And we get, again, a reduction by 2. Okay, so reduction in power by 2. And the last one, I'm not going to do cotan or cosecant because we can usually convert those to something else. I'm going to give you the tangent one just in case we need it. So often when we get like powers of cotan or powers of cosecant, we usually just convert them into either powers of secant or powers of tan, and then just use, so the 4 reduction formulas we have pretty much do all of the trigonometric powers. Okay, the tan one looks a little strange because it doesn't really involve anything other than itself. Okay, so the first step here is to get that uv part. So 1 over n minus 1 times tan to the n minus 1. And then we're going to get a subtraction and a reduction in power, again by 2. Okay, let me check restrictions. Sine and cosine are fine. Tan is going to have a restriction, and secant has a restriction as well. So, okay. So obviously the tangent reduction formula is not going to work for n is equal to 1. And I think the same thing happens for secant too, right? So in our formula up here, obviously, n can't be equal to 1. Otherwise, you're going to get division by 0. So I think pretty straightforward restrictions on these reductions. Okay, is there anything else I need to do? Yes, I have one more integration by parts example that we need to do. And that's going to get us into a pretty good place. Then we can pretty much get to ArcLink. Cool. But we'll do that Wednesday. Okay, let's take a look at one final integration by parts example to finish off class today. The reason I think it's a good idea for us to look at this is because if you do try to put this into the integral calculator, you're going to start to get like potentially weird fractions popping out, and you're going to be like, why? What's happening? Help. So I think it's worthwhile for us to look at one of these weird cases, and it really actually stems from what we did back here. So if we look at the proof for the reduction formula here at the highlighted part, I said, hey, we're going to have to add these integrals together. So we had like the integral of secant plus n minus 2 copies of the integral of secant, and we combine them together. This is something that does come up working with more general integration by parts problems. So I want to give you an example that's not like a proof of a reduction formula. And the easiest example we can take a look at is, when we multiply something like e to the x times cosine of x. Looking at this integral on its own, there's no substitution that's going to be helpful. I can't pick u equals e to the x or u equals cosine of x. Those are not helpful substitutions. So the next best tool we have is to try to tackle this using integration by parts. And if we want to tackle this using integration by parts, we have to decide which part we'd like to play the role of u. And that's weird. And which part we'd like to play the role of dv. Who would you get to play you if we had to make a movie of your life? Who would play you? E to the x would play me. Tom Cruise. Why are you crazy? Like you just want to jump on couches and dance? Friend of Oprah? Is that what's happening? Excellent. Oh yeah, I forgot about that. Yeah, all the mission, was it all the Mission Impossible stunts were done by him, which is kind of cool. I want to dance for. Who doesn't want to dance for Oprah? I would dance for Oprah. She like came up to me and she was like, "Dance." I would dance. Especially if she had a gun and she was like firing at the ground. I'd probably dance. Okay, so Damien is making a suggestion for, maybe she'll give everyone a car. Damien's making a suggestion for what we could use for u, and that's e to the x. Sure, let's roll with that. So let's take e to the x as our u function, which means the leftover stuff, cosine x dx, would be our dv. Okay, let's go ahead, find the derivative and antiderivative. Okay, obviously the derivative of e to the x is itself. And the antiderivative of cosine is sine. Okay, so with that, we have the essentially three pieces that we need in order to use the integration by parts formula. This is going to be u v minus integral v du. Okay, so u v, we get e to the x sine x, a minus integral v du. And we run into this like crap moment where we're like, damn it. I have used integration by parts and it does not look like anything helpful has happened. But yes, Damien is giving us a shred of hope. He says, you know what? Hold up. Why don't we just try it one more time and see what happens? Maybe it'll be good. Maybe it won't be good. But let's just give it a shot. And I'm going to kind of be mindful just to take the same function as u. So don't cross paths here. If you've started with u equals e to the x, keep using u equals e to the x. And that means the leftover stuff, sine of x dx, is going to be our dv. Okay, we've already taken the derivative. We know that our du is going to be e to the x dx. Now over here, we might have to be a little careful with negative signs. Is this going to be negative cosine, I think? Right, negative, the derivative of negative cosine is positive sine. I think that's right. Okay, excellent. So with all of that over on the right-hand side, we're going to apply our integration by parts formula one more time, but we're going to apply it just to this. Okay, so in other words, I still have this e to the x sine x business. I have a minus sign, and then I'm going to kind of be putting this into here. So I need to be careful here. It's the negative signs. They will ruin your life. Okay, so u times v minus v du. Okay, so I'm going to put some squarey bracket boys here. Okay, square brackets, because I do need to distribute this minus sign through, but I want to kind of clean up some stuff inside here as well. So let me do a little bit of housekeeping. That looks good. And then this will come through here and we'll get e to the x cos x dx. So that's what hopefully the housekeeping is going to look like after I deal with all of those negative signs. And I think I'm in a good place. Yes, that seems reasonable. Okay. I mean, if you don't know what's happening, you're going to look at this over here and go like, fuck. Nothing looks good. Nothing looks good. But wait, the left-hand side, we started with that exact same thing. So what we could do is we could add these two things together, and then that should let us finalize the problem. So what we're going to do is we're going to add these two together. And that will help us finish the problem. So over on the left-hand side, we have one copy of this integral. Moving the other copy over, we're going to have this. And that's going to leave us with something that looks like e to the x sine x plus e to the x cos x over on the right-hand side. Okay, this is one copy of the integral. This is one copy of the integral. So we should have now two copies of this integral. And then our last step is to divide both sides by 2. And I'm going to throw in a plus c just for good measure, because if we do want a generalized antiderivative, we do need that constant of integration as well. So there you go. There's a more, I think, realistic kind of example where working through integration by parts kind of cycles you around to the starting integral. And then to finish up the problem, you have to add those integrals up. So that's a very common thing. If you're working on like some textbook questions, they'll throw a couple of these into the mix just to make sure you're on your toes. Okay, so that's kind of what I wanted to cover for today's class. Let's see, I'm going to throw up our, I'm going to just period. I'm going to throw up today. It was a hard class today. So if you're feeling a little anxious, I get it. Start doing some more practice out of the textbook. And, use the integral calculator to help you if you kind of run into some snags. But the real key for this course is, yeah, sorry, Kate. I'll share this as I'm opening some stuff. So the real key to this course is just making sure you do enough practice that you kind of know how to start problems. That's really the key, right? I don't want you to look at a problem and go, I don't really know how to start that. It would be nice to know how to start stuff, essentially. If you need to utilize The integral calculator, that's fine. I mean, it's online. You have access to that, so no worries. And the last thing I want to just let you guys know of before you start clocking out is the second. I was a busy boy this weekend. We got assignment number 2 posted. So you can start working away at assignment number 2 on WebAssign if you would like. It's going to be due the Sunday of reading week. So you should, I think, be able to do all of assignment 2 right now. So you can start working away at that. And if you get it done before reading week, that's great. But it's due the Sunday of reading week. So you have a lot of time to work on this second assignment. I have also posted up the 4th quiz for you. That will be due by Friday this week. The 4th quiz is mostly working with volumes and a little bit of work with integration by parts. There is one question that I want you to do by hand and upload it to this Dropbox, okay? So the final question on this particular quiz, question number 7, is going to have you try to set up an integral for the following shape. And then I would like you to solve that and just upload it to this particular Dropbox. It depends on the quiz, Nathan. So most of the quizzes Moodle will mark and I will not mark. So if there is a problem, please just let me know via email and I can go in and check stuff. Because sometimes when I'm coding, sometimes when I'm coding, I make mistakes. So it happens. So if you think something's incorrect, just let me know and then I will try to fix that. I don't trust Moodle. Like you should be able to go back and look at the correct answers. That's kind of what I would like to do. So yeah, you should be able to go look at your previous quizzes, check and see if things make or don't make sense. And let me know if they don't make sense, and I'll stick around because we have a bit of time if you guys want to look at something specific as well. But usually you won't be able to see your quiz until after the due date, right? So you should be able to check quiz 3 now because it's after February 5th. If you go to do quiz 4, you're not going to be able to look at it till after the 12th. That's how I set it up. Okay. Have I answered everyone's questions? Yeah, so please, question number 7 on this next quiz, do that by hand and upload that. Just drop it off into the Dropbox for me. And there's also a potential here for some bonus marks as well. So quiz 4 is one that I'm going to mark. I'm going to go through and mark question 7 essentially by hand. Okay, so with the online textbook, so like the WebAssign stuff, do you have the WebAssign textbook, Colin? Okay, I'll see if I can find it. I don't usually use you might have to show me where the online textbook is. Yeah, if you guys got places to go, then please, by all means, jump out. And have a lovely rest of your day. And I'll see you Wednesday. If we Gucci. Okay, so this is the ebook. Let me know, Colin, if this looks similar to yours. You're welcome, Sebastian. So like, is this what you have, Colin, like this? Okay, cool. So we have been kind of working through chapters like 5, 6, and 7. We're kind of doing a bunch of stuff at the same time. So if you want some practice on integration by parts, this is inside the techniques of integration section. Okay, there it goes. So what I'll do is I'll try to get you chapter titles. So integration by parts. So 7.1, and then you can go right into the exercises. So we would have done a bunch of indefinite integrals. We saw the reduction formulas, and you can find some exercises inside of 7.1. So let me throw that. We'll do that in the chat. Oops, 7.1. So that's one of the chapters. Nope. That's probably not what I wanted. I probably hit the wrong button. You can tell how often I use can tell how often I use WebAssign, but I'll use my hard copy because it's going to load a little bit faster, and I'll let you know what sections you should be doing some practice out of. So anything from chapter 5 is good. You should be able to do, most of chapter 5. I would go like 5.3 to 5.5 is what I would do from chapter 5. Like the fundamental theorem of calculus, you guys can get some more practice with that. The substitution stuff, you should be able to do more with that. We've done areas between curves, which is 6.1. We've done volumes, which is 6.2, 6.3. So those are good. And we've done 6.5 as well. So we've covered all of those from section 6. We are not going to cover 6.4. Just so that we have enough time to cover sequences and series. And then we've done 7.1 as well. So those are the chapters that we've kind of covered so far and where you should be focusing your attention when it comes to doing a little bit extra work. Yeah, no worries. Okay. Anyone else want to stick around to do anything? Let me know in the chat. Otherwise, we will... For number 4, I got the 4 and 6 mixed up. On the quiz last week. Can you just email me, Amy? Just email me, let me know, and I'll take a look at it after class this afternoon, okay? Yeah, when it comes to like little stuff like that, like those little things where you've made a mistake, but you've just submitted the quiz and you can't go back, just email me. Can we go over? Yeah, we can go over your quiz. I'm just going to wait to see if anyone else has any business. I'd rather them not also see your quiz. I am going to actually, let's stop this as well.